We'll be starting today's session from where we left off yesterday. In algebra, there was one topic which I did mention that we have sort of left out. So I'll cover that today, and then we will move to the next topic, that is plane geometry. So in the algebra part, one of the components that was left out was linear equations. And yesterday we did discuss that whenever we have the power 2, we refer to it as a linear equation, quadratic equation. And whenever the power or the highest power is 1, we refer to that as linear equation. Now, linear equations are very straightforward to solve, but if they are in 2 variables, that is where, or 2 or more variables, that is where this can become very interesting. So one thing to remember is whenever you are solving a linear equation, you need as many equations as there are variables. So if I give you an equation, let's say a plus 2b is equal to 4. Now this has 2 variables, a and b. These values can change, right? Now in this equation, a plus 2b is equal to 4. The values can be altered, but you will not know which is the unique solution that you're looking for. And if you start plotting these value points which satisfy this equation along the graph sheet, you will see that it will sort of form a straight line. So just let's do one sample. If you take a and b, right? If a was 0, b would have been equal to 2. If a was 1, b would have been equal to 3 by 2. If a was 2, b would have been equal to 1. And if a was, let's say, minus 1, b would have been equal to 5 by 2. And if a was minus 2, this would have b would have been equal to 3, correct? So let's say if you plot these points, sorry, if you were to just plot these points along the graph sheet. So let's say if a was 0, b was 2. So it was somewhere here. This is 0, 2. If a was 1, this was 3 by 2. So it will be somewhere here. 1, 3 by 2. And if it was 2, it would have come to 1. So this is 2, 1. And if a was minus 1, if it was minus 1, it was somewhere here. Minus 1, 5 by 2. And if it was minus 2, it would have gone somewhere here. It is minus 2, 3. So if you observe, all these points can actually be joined along a straight line. Okay. Now remember that in between these points also there are several points. In between the points which I have plotted as well, there are infinite number of points which will satisfy the expected condition. So this straight line is referred to as a locus of points which satisfies the condition a plus 2b is equal to 4. So what is a locus? Locus is a collection of all those points which satisfy this condition. Let's say you are defining a circle, for example. A circle is a collection of all those points which are there at a particular distance, at a fixed distance from a given point which acts as a center, right? So if I fix this as a center, collection of all the points which are at the same distance from the center will form a circle. So though my drawing is bad, this concept of locus is something which is very useful for all of you to understand. Now, once you have defined all these points, once you have defined all these points, if I just give you one equation, if I just give you one equation, that is a plus 2b is equal to 0. Now, if I ask you how many solutions or how many sets of values are there such that they satisfy this equation, how will you define that? How many sets of values are there such that they satisfy this equation?
Infinite.
Yes, there are infinite number of values, right? Now, suppose I give you another straight line or another linear equation in two variables, which was like this. Let's say this was another equation. Okay. Now, how many sets of values are there which satisfy both the equations?
1.
There is only one unique point here. Correct? If I give you a scenario where this line was parallel to this, then
No solution.
no solutions at all. There can also be another condition where the given equation is 2a plus 4b is equal to 8. Then if you substitute the values here, let's say a was equal to 0, then what will b be?
2.
B will be 2. Okay, if a was 1, then
3 by 2.
again b will be 3 by 2, and so on. So if you see, just by multiplying this entire set of equation, that is a plus 2b is equal to 4, if you just multiply it with by any number. Now in this case I have multiplied it with 2. If you multiply it with any number, so I can write a plus 2b is equal to 4. If you multiply it with any number, any constant number, you will get back the same equation. And if you plot the graph, you will represent the same straight line. Okay. So there are three scenarios which have come up now. One, the general form of an equation, we write it as ax plus by plus c is equal to 0. Okay. Now, if you take the first equation, a1, b1y and c1 is equal to 0. If the second equation was a2x plus b2y plus c2 is equal to 0, there are three possibilities which arise out of this. The first one is there is a unique solution. When is this unique solution? When can I say that the lines are not parallel? Am I right?
Yes, sir.
Whenever the lines are not parallel, you will see that these two lines will intersect on the graph, and so they will have a unique solution. The second one is there is a possibility of no solution at all. When is this going to happen?
Parallel lines.
When the lines are parallel. And there is an interesting property which says, we will not be going into great detail today, but you will see that how it works. It says that if the lines are parallel, then the coefficients of a, x and y will be equal, which means you can write a1 by a2 will be equal to b1 by b2. They will be in the same ratio. Okay. Or in some cases, if you sort of further simplify it, you might be able to write down a1 is equal to a2 and b1 is equal to b2. That's a real special case scenario. The third one is when there are infinite number of solutions. Infinite number of solutions. When will this happen? Infinite number of solutions.
When there are coincident lines.
When they are coincident lines. And I mentioned they are coincident lines. If you take one equation, just multiply it with some constant, you will get the next coincident line, right? So you can write a1 by a2 is equal to B1 by B2 is equal to C1 by C2. Now, if you observe, this condition is very similar to the second case of no solution. That is why we clearly add that this should not be equal to C1 by C2. Because if they become equal to C1 by C2, then they'll have infinite solutions. Okay. Now, given any set of equations, you will have to constantly keep checking whether any of these conditions is being valid or not. And if it is not working, then you will have to go back, review that set of equations which you have, and then finalize the types of solutions. What are the solutions that are asked, and you can always you know how to solve a system of linear equations. I will not get into those details as much. Okay, any questions at this point? So this particular concept, yesterday we did discuss about quadratic equations, and now we are discussing about straight lines. One of the interesting things is both of these concepts actually act as a bridge between algebra and coordinate geometry. Coordinate geometry is a part of geometry where we deal with this coordinate axis, where you are basically dividing the entire plane into several small pieces that you can attach an address to. That address is what is called as the coordinates, value of the coordinates. Okay. Any questions at this point? Okay. So now we'll move to the next topic, that is plane geometry, which is the topic that was assigned for today. What all did you study in school when we discuss about geometry or plane geometry? Yes.
Geometrical figures, circles, triangles, coordinate geometry.
Yeah. So today, in today's class, we will primarily be discussing about triangles, quadrilaterals, and circles. I'll not be going into great detail with specifically with respect to coordinate geometry. If time permits, maybe towards the end of the class, I'll spend some time on one or two problems in coordinate geometry as well. Okay. Now, whenever you are given any plane figure, now depending on the number of sides, we classify that as a triangle, a quadrilateral, a pentagon, and so on, right? Now, most cases, whenever we are talking about any polygons, polygon means multiple sides, right? 3 or more. Whenever you have a closed figure, you will have a polygon, right? So whenever you have a polygon, how will you calculate the interior angles? How do you calculate the interior angles, the sum of the interior angles? Yes. Any idea?
So sum of exterior angle is always equal to 360 degree.
Okay. What about the
So-
interior angles then? So can you do you know how to prove that the sum of exterior angles is always equal to 360 degree?
So by taking examples.
So one, if you need a mathematically rigorous proof, you just, taking examples is not the only way. Now, you know how you can mention that sum of the angles in this triangle is equal to 180 degree. Am I right? This
Yes, sir.
sum of these three is 180, right? So you would have studied this in school. So I'll not go into detail of explaining this. But the moment you have a quadrilateral, can you see that you can break this down into true triangles?
Yes, sir.
So here, the sum of angles in the first triangle will be 180, and then there is a second triangle here. The sum of angles is 180. So together, total, let me say sum of angles. So together, all the angles together will be equal to 360 degrees. Right? When you have a pentagon, what will you do now? Pentagon, you can again divide.
Three triangles.
Yeah, so you can again divide into three triangles. So this will be 180. This will be 180. And this will be 180. So together they'll be equal to sum of angle, all angles here will be equal to 540 degree. Am I right?
Yes, sir.
So how many triangles are formed? If you are dividing a polygon, if there is a polygon with n sides, how many triangles are formed?
N minus 2.
Yeah. So can I say that the sum of all angles will be equal to n minus 2 into 180 degree?
Yes, sir.
So this is one easy way of calculating the sum of all angles in a quadrilateral or in any polygon for that matter, not just a quadrilateral. Okay. Now, another interesting question that can be asked is how many diagonals can you draw? Let's say you take a quadrilateral. You know that there are two diagonals here. But in a pentagon, how many can you draw? Yes, how many are there now? 1, 2, 3, 4, 5. Am I right? Rest all we
Yes,
have
sir.
anyway counted, correct? So how will you predict how many diagonals are there? So to calculate the number of diagonals, there is one very interesting logic which will help you calculate. So if you calculate the number of diagonals, you basically draw the diagonals from the vertices, no? So how many vertices are there? Number of vertices is n, right? From this, to how many vertices can you draw the diagonals? If you are starting from here, you can't draw a diagonal to this place. You can't draw a diagonal to this place. You can't draw a diagonal to this place. So how many diagonals can you draw? You can draw to n minus 3 diagonals. Am I right?
Yes, sir.
But if you observe this, let's say take this diagonal. In this direction, you are counting once. And when you come to this point again, going backwards, you will say that I can count backwards also. Right? So each diagonal you would have counted twice. So the number of diagonals will be half of n into n minus 3. Okay. Now if you substitute that case of a triangle, number of diagonals is how many diagonals can you draw?
0.
0. The moment you substitute 3 sides here, you will get 0. If you substitute a quadrilateral, if you substitute n is equal to 4, then how many diagonals can you draw?
2.
2. How many diagonals can you draw in the case of a pentagon?
5.
5. That's exactly what we have counted also. Right? There is another interesting case when you have, let's say, a regular hexagon. Okay. What is a regular hexagon? What does that mean? The word regular, what does it mean?
Every sides and every angles are equal.
Yeah, all the sides and all the angles will be equal. So if you take the regular hexagon like this, and if you start drawing, my drawing is pretty bad. Yeah. So if you start drawing all the sides and the diagonals, you will see that they will all coincide at one point. In the case of a regular hexagon, what is very interesting is all these sides also will be equal. So each of the triangles which is formed will also be a equilateral triangle. Okay. Now, what is the length of this diagonal? What will be the length of this diagonal? Can you see?
Equal to the side of the hexagon?
It is equal to the twice the side of the hexagon.
Yes, sir.
So if this was A, this would have been 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 A. So the length of the diagonal would be 2A. Am I right? And now if you extend outwards these two sides, you will get another equilateral triangle with all sides A again. Right? So it is almost like this big triangle. This would have been an equilateral triangle with sides 2A. You are cutting it here and then folding this. Right? So there are lots of interesting properties like this which can arise out of some regular shapes. And sometimes there are questions which are asked along this. But all those properties of a quadrilateral can definitely be studied if you just study the properties of a triangle. Okay, so all the properties of a quadrilateral can definitely be understood or studied if you just understand the properties of a triangle. So we'll spend some time looking at the properties of different triangles. Okay, now let me take the case of an isosceles triangle. So let's take this is an isosceles triangle. So can I say that these two sides will be sides and their opposite angles are equal?
Yes, sir.
Okay. Now let's say if I draw the median here. If I draw the median here, can you guess what this angle will be?
90 degree.
Why would it be 90 degree? How can you say that it will be 90 degree?
Sir, because first of all, AB is equal to AC.
Okay.
Angle ABD is equal to angle AC.
Correct.
BD is equal to CD.
BD is equal to CD. Okay.
SAS congruency criteria, both the triangles are congruent.
Yeah. So what are the triangles? So you will say ABD is congruent to triangle ACD. Am I right?
Yes, sir.
By SAS. So the moment you say this, can I now say angle ADB will be equal to angle ADC?
Yes, sir.
So let's say this is equal to X. You also know that angle ADB plus angle ADC is equal to pi or nothing but 180 degree.
Yes, sir.
So X plus X would be equal to 180 degree. So X is equal to 90 degree. So now the moment you write this down, you can say that in an isosceles triangle, In an isosceles triangle, this median, the median to the non or the unequal side will be nothing but the altitude. It will be the perpendicular bisector. Will it also be the angular bisector?
Yes, sir.
Because these two angles will be equal, no? By congruency. And this will also be the angular bisector. Okay. However, will I be able to say the same thing if I draw a median here? Let's say I call this as E. Can I say something similar about the median BE?
No, sir.
You will not be able to say anything there. Okay. Similarly, if I draw the median CF, again, you will not be able to say anything very similar there. Okay. So in a isosceles triangle, the interesting properties are all around the altitude or the median, which is drawn from the unequal angle to the unequal side. Okay. So what will this point be? The point of intersection of all the medians. What is it called?
Centroid.
It is called the centroid. Okay. What are the properties of the centroid? What does the centroid do? Anything interesting?
Sir, it divides the median into 2:1 ratio.
Yeah, so usually we give the notation AG, G for the centroid. So AG will to GD will be in the ratio of 2:1. Okay, so you should also be able to predict the dimensions of these. In this case, like let's say you are calculating the area of triangle ABC, you will write half AD into BC. Am I right? Because AD is the altitude, it can act like the height.
Yes, sir.
Correct. So can I now say half? What is AD? AD is nothing but AG plus GD. Into BC. And what is AG?
2AD.
Not 2AD, 2GD.
2GD.
2GD, right? So you can write half 3GD into BC, or if you write GD as half of AG, can you then write half into 3/2 into AG into BC? So if you observe the same area formula that we were writing here, AD into BC, can also be written in two different forms. Because we now know the dimensions of AG and GD. But remember, this will only happen in the case of an isosceles triangle, because here the median is also working like the altitude. So sometimes in NTSC, they have these questions. They'll ask you to calculate the area of triangle ABC is, and they'll give you some 4 or 5 options. You'll have to choose which is the right option, and they might be similar to this, similar to the two forms that we have just calculated. So you should be able to sort of understand which form suits the requirement here. Okay. Similarly, a lot of interesting properties when it comes to the equilateral triangle also. So in an equilateral triangle, whatever we wrote here, saying that the median, bisector, altitude, perpendicular, bisector, will be the case for all the sides, all the altitudes, all the medians. Okay, so sometimes there are questions which are asked around that as well. And in the case of an equilateral triangle, you will see that the centroid, the circumcenter, the orthocenter, they all coincide. Okay, so if you take a equilateral triangle, you will be able to draw and this is called an incircle because this is inscribed inside. Okay, ideally this should have been touching here, and when you draw it will be perpendicularly. So this point will act as the incenter, this will act as the centroid, this will act as the circumcenter, this will also act as the orthocenter. Okay, what does it mean that what do you think it means by saying that this is a circumcenter? Because there is a circle which can circumscribe this triangle, meaning it can go around this triangle. Okay, now my drawing is so poor that this does not look like a circle, but this center, if you draw a circle with this radius, then it will go around the circle, right? So there are some interesting questions which can be asked here. So let me erase this very ugly drawing. Okay, now if I ask you capital R is equal to radius of the circumcircle, how much will that be equal to? Can I say that this is the radius of the circumcircle? AG?
Yes, sir.
AG, right? This is nothing but 2/3 of AD. Am I right? And if you observe this AD, triangle ADC is a right angle triangle. So can I say AD square plus DC square is equal to AC square? So AD square, what will be the length of DC? Will it not be equal to half of the side?
Yes, sir. Half of the side.
AC square will be A square. So what is AD square equal to? It will be equal to A square minus A square by 4. So it will be 3A square by 4. So AD will be equal to square root of 3A by 2. Am I right?
Yes, sir.
Now if I bring it back and substitute it here, 2 by 3 into root 3 by 2 into A. 2 and 2 will get cancelled. Root 3 will be left in the denominator. So A by root 3. Okay. So what does this mean? This is the radius of the circumcircle will be equal to A by root 3. Okay. Now what will be the radius of the incircle? Radius of incircle. small r is equal to, can I write GD?
Yes, sir. 1/3 AD.
Yeah, so it will be 1/3 times AD. So AD we already know, √3/2a. So a by 2√3 will be the radius of incircle. It is not necessary to remember all this. I'm just showing what type of problems can be asked and how you can quickly calculate all those, even if you don't remember any of this. Okay, so this radius of the incircle, small r, is equal to a by 2√3. Okay, now suppose if I take out, let's say I remove this part of the diagram. Suppose I remove this part. So let me just draw this part on the left side. Whatever this is there, no? This part if I draw in a slightly different manner. Hmm. Okay, now this was side B. Just look at this. I have just turned this a bit. This will be point D, and if you know, this will be F. And the center of the circle is G. Now in circles, you would have studied about tangents. Now if you look at this figure, isn't this BF and BD, aren't they tangents? BF and BD, aren't they tangents?
Yes, sir.
Yes, sir, they are.
Now if I join this here, BG, right? And if I join this like this, GD, and you know that they are perpendicular,
Yes, sir.
Yes, sir.
and you know that GF is equal to GD. This is nothing but the radius of the incircle. Am I right?
Yes, sir.
Yes,
So now can you see that triangle BFG is congruent to triangle BDG by RHS congruency?
Yes, sir.
There is a right angle. Hypotenuse to BG is common for both. And then there is a side FG and DG, which is common for both. Right? So can I now say that BF is equal to BD?
Yes, sir.
Right? Now this one, this particular statement, BF and BD, you would have studied in a totally different context in circles, where you would have said that length of tangents to a circle from an external point are equal. Am I right?
Yes, sir.
So if this point B was there, which is outside a circle, so if you have a circle like this, if there is a point here, from here if you are drawing two tangents like this, you will say that this length and this length, they both are equal. How do you prove that? What you have to do is just connect them to the center and draw the central line Now you know that the tangent and the radius are always perpendicular to each other. So you will have two right angle triangles which are congruent to each other by RHS congruency. Then automatically you will see that the length of the tangent on both the triangles, they will become equal. So this is a very, very interesting or a very useful property, which is also covered in circles. But if you say this is actually part of a special case scenario in when you take a triangle, an equilateral triangle, and draw an incircle. So in an equilateral triangle, what is happening is this will become 60 degree, the angle at B, right? But in reality, this need not be 60 degree. This can be any angle. Okay, this can be any angle, but this will this congruency will still be correct, and the length of tangents will be still be correct. Length of tangents will definitely be equal. So as this point comes closer to the circle, you will see that the angle becomes bigger and bigger. Right? If that angle was 90 degrees, you will see that the length of the tangent will become equal to the length of the radius. So if this point is moving closer to the circle, it is almost like the tangents are opening up like this. If it is moving away, the tangents will close to each other. That angle will become smaller. Okay, so in circles, you will have some very interesting questions around tangents which are asked. So 2-3 things which you have to always remember. One is, if you take an external point from the circle, length of tangents will be equal. That is one thing. Next, from the center of the circle, whenever you draw a line to the foot of the tangent, that is always the radius, and it will always be perpendicular. Okay, so this angle will always be 90 degree. This is something which you also have to understand. Okay, so there are multiple cases like this which you will sort of have to keep track of, and there can be some interesting questions asked around the tangents or around chords also, right? Now if you take another scenario, let's say this is a circle, and if you draw a chord, let's say this is center O, this is chord AB, and there is a point here C, and let's take another connection. So can you say something about angle AOB and angle ACB? Is there a connection between these two?
Angle AOB is equal to 2 times angle ACB.
Yes. So how will you prove that? This is correct. Whatever you have mentioned, that it will be twice this angle, that is correct. But how will you prove that? Any guess how you can prove this? Let me also ask one more question. Let's say there is a point D here. Can you say something about angle ADB and angle ACB?
So they both will be equal.
They both will be equal. Yes, very good. How do you know that they both will be equal? You would have studied something around this. Have you studied that a chord subtends the same angle?
Yes, sir.
Yes, sir.
So if you take this chord AB and if it is subtending any angle in the major segment, whether at D or C, the angle will always be equal. Correct?
Yes, sir.
So how do you prove this? How will you prove this? Yes. Any guesses? You might have studied this in school. My guess is, especially in the chapter of circles, you would have definitely studied about this. Okay, so in case you don't know it, I would suggest that you go back and sort of quickly revise this aspect of how you can prove it. Usually NTSC, there will not be questions on prove that so and so is that. However, it is important to know how you have arrived at this logic, because it can be applied at other locations. Okay, so remember that in the major segment, if you take a chord AB, it will always subtend the same angle. So this angle will always be equal to this. And in fact, this is not, even if you take something like this, if this was an point E, again, this angle will also be equal. So in the major segment, the moment you draw the chord, any angle that you draw, it will always be equal. Okay.
Yes, sir.
And the interesting part is, if you're drawing that angle in the major segment, always remember that this angle is acute. And you should know that this will always be less than 90 degree. If AB was the diameter, then this angle would be exactly equal to 90 degree. Okay. And if AB was if you're drawing it in the minor segment, if you're drawing this angle in the minor segment, then this angle would be greater than 90 degrees but less than 180 degrees. It would have become an obtuse angle. Okay, so if I draw something here, like in the minor segment here, AF, angle AFB will always be greater than 90 degree, and it will always be less than 180 degree. So it will be an obtuse angle. Okay, so you should know how we have arrived at this conclusion. You should know how we have arrived at this conclusion. Okay, that is very important for you to be able to sort of decipher all these conclusions, especially this result. That this result is also something which is very, very useful and important. We will be repeatedly using this in several of our geometrical proofs. Okay, any questions at this point? Okay, the other interesting questions are which can be asked are a result of questions like mensuration. Right now, you might have come across geometrical shapes. Like for example, the moment you are given a triangle, if I ask you the area, you will say half base into height, where this will be the base, and you draw a perpendicular here, and you will say that that is the height. Right now, if I now change, let's say, if I draw another triangle here, right, and let's say that they both fall under the same parallel lines, what will the height be? Height will remain the same, no? Because they
Yes,
are
sir.
parallel lines. And in both these cases, you are seeing that the base is also equal.
Yes, sir.
So can I now say that between two parallel lines, the area of a triangle subtended by a line segment will always be equal?
Yes, sir.
Yes, sir.
So even if I extend like this, let's say you draw a triangle like this. Again, height is same, base is same. So triangle area will always be equal to half base into height. Or if you take it to some extreme like this, again it will continue to remain half base into height. Right? So if you have two parallel lines, and if you take a line segment AB, the triangle which is subtended by this line segment AB, irrespective of how this triangle looks like, the area will always be equal. This is one very, very useful result which we can always apply. Okay. Now, where is this half coming from? Area of a triangle, we always use half base into height, no? Where is this half coming from?
Sir, from parallelogram.
Yeah, so what we are actually doing is we are drawing a parallelogram. So what we are essentially doing is we are taking two parallel sides. So you have two parallel lines like this. So we are taking this segment AB, and then you take another segment which is of equal length, DC. And now if you are joining these two, okay, now the result is a parallelogram. So if you need the area of triangle ABC, can I say that this will be equal to area of the triangle ACD?
Yes, sir.
Yes, sir.
How will you say that? How can you arrive at this result?
As in parallelogram, the opposite sides are equal.
Correct. So this side is equal to this side. These two sides, this. Yes. So,
So height is always equal in case of two parallel lines.
yes. So what you will be doing, what you are actually doing is you are saying ABC is congruent to CDA. Can you see this?
Yes, sir.
Yes, sir.
Which is the congruency that we are using here?
SSS.
Side.
Yeah, we are using triple S. We can also use SAS if you observe, because the opposite angles are equal, no?
Yes, sir.
We can also use SAS. We can use ASA also, because this angle will be equal to this angle. Right? So then I can say, because these two triangles are congruent, I can say that area of triangle ABC will be equal to area of triangle CDA, which means area of the quadrilateral ABCD would have been equal to area of triangle ABC plus area of triangle CDA. Isn't it? I am dividing this parallelogram into two parts. So the total area would have been equal to sum of two pieces. Now, this is nothing but area of triangle ABC plus CDA. We have already mentioned that this is equal to area ABC. So you will write ABC. So what does this mean? Area of triangle ABC is equal to half of the area of the quadrilateral ABCD. Now, how will you calculate the area of this quadrilateral? You will now draw a perpendicular. And then you will say that if you draw a perpendicular here, you will say that these two are equal in area. Am I right?
Yes, sir.
Yes, sir.
Basically, you are using RHS congruency for these two triangles. Let's say this is E, this is F. So can you say that triangle AED is congruent to triangle BFC? I am using RHS congruency. Because there is a right angle, the common side which we are using is DE and CF, which is the height or the gap between two parallel lines that is anyway equal. Hypotenuse in both cases is the opposite side of a parallelogram, so that is also equal, correct?
Yes, sir.
Yes,
So
sir.
I can say area of triangle AED is equal to area of triangle BFC.
Yes,
So
sir.
now I can say area of quadrilateral ABCD will be equal to area of EFCD. Am I right?
Yes, sir.
And EFCD is nothing but a rectangle now, right? So area of this rectangle is equal to EF into CF. And this EF is nothing but AB into CF, base into height. So this you would have now written as half base into height. Any questions around this? Now, once you know one way of breaking down this complex shape into triangles and then looking at congruency and so on, there are usually lots of questions asked around mensuration of or using simple shapes as triangles. So what you will be doing is, let's say you have a complex shape like this. Let's say you have a complex shape like this. There are no, let me say there are no sides which are equal. And if I give you a question where I ask you to calculate the area of this shape, then what will you do? How will you calculate?
By using Heron's formula?
Heron's formula can be used for a triangle, right? Like if you divide this,
Dividing it into two triangles.
and if you know this diagonal, then you can use Heron's formula. And then you will calculate the area of these two, right? The other way of solving this, or let me say, if this shape was a bit more complicated, what if this was like this? Then what would you have done? How will you solve this now? So when you have questions like this, what we should be doing is we should be dividing this shape into shapes, basically triangles, rectangles, or trapeziums that we know how to handle. Let's say you draw a perpendicular here This is a right angle triangle which is easy to calculate. This is a right angle triangle which is easy to calculate. Let's say you draw a perpendicular here. This is a right angle triangle which you can easily calculate. You draw a perpendicular here. So this will be a right angle triangle which you can calculate. What about this shape which is left out? Can you see that this is a
It is a
trapezium?
trapezium.
It is a trapezium. So you can calculate the area of this trapezium also. Right? So however complex any shape is, you can always break it down into pieces which are either triangles or trapeziums and then calculate the area together. So sometimes there can be questions on mensuration, especially on areas, which can be asked around this. The last part to discuss is basically when you have three-dimensional shapes, and then there is mensuration, that questions which can be asked around that as well. Most of them are direct application of formula. So let us spend a few minutes on that. Let's say you have a cube. So if I ask you what is the volume of this cube with the side A, you will say that the volume will be equal to a cube, and the surface area will be, each surface has a square as the area. So the total surface area will be 6a square, right? Now, but if you have a cuboid, like let's say a sweet box or a shoe box, where there are different dimensions. So this will be the length, height, and the breadth. So in this case, the volume will be equal to LBH, and the area will be equal to 2 times
LB plus BH plus HL.
Yeah, and sometimes you are also given the case of a cylinder. Now in the cylinder, there is a height and then there is a radius. So volume will be equal to
Pi r square h. Pi r square h.
And area will be equal to
2 pi r h plus 2 pi r square.
2 pi r h. And this is the area of only the curved surface, but at the top and at the bottom, there are two other circular areas. So you will have to calculate or add those two also. So 2 pi r square. So when, and here they might refer to as a curved surface area. When they refer to the curved surface area, you will write only 2 pi r h. When they are saying total surface area, you will add those pi r square as well, right? Then you have a case where you have a cone. So in the cone, the volume will be 1/3 of the area of a cylinder. So it will be pi r square h. And what will be the area? Area will be equal to pi r l, where L is this length, the slant height. And if they are saying total surface area, then you have to add this area at the bottom also. So it will be pi r square. Okay. You are also given a, yes, yeah.
Sir, for the surface area of cylinder, there is a formula 2 pi r h plus r. Is it correct?
Yeah. So the same thing. If you take 2 pi r common here, 2 pi r, if you take common here, h is left, and then there is an r here. That's how you are getting that formula.
Okay, sir.
Okay. So I've written the same thing here. Okay. Now, if you have a sphere, the volume, you will write it as 4/3 pi r cube. And if you are writing the area, you will write 4 pi
4
r.
pi r square.
Yes. So here, if you are, let's say, cutting half of it, if you are cutting it into half, you will get a hemisphere. Hemisphere is half a sphere. So there, what will be the volume? Volume will be half of 4/3 pi r cube. So it will become 2/3 pi r cube. What will be the area? Area of the curved surface will be pi r square. 2 pi pi r square. And then when you're cutting it, there's also a circle which is formed, right? So you'll have to add that also. So then it will become 3 pi r square. Lot of questions are asked around this. So if I increase the radius by so much, what will happen? If I convert this cone into a sphere, what will happen? If it is made of a metal, I break it down. Let's say there is a big ball of metal and I break it down into small balls. How many balls can be formed? So all of this are questions which are just based on this simple play of numbers. So I'm sure you will be able to solve any questions which are asked around this. So mensuration and plane geometry that way are topics where you will definitely be asked lots of questions, and you will also be in a position to solve all the questions. The only thing you have to be careful about is read the questions carefully and draw free diagrams or draw rough diagrams whenever needed. Okay, so I'll stop here. If you have any questions, you can ask. Otherwise, I'll hand over to Maitreyi. Any questions from anyone?
Sir,
Yes.
sir, if in a circle there is a secant and there is a tangent,
Hmm.
then what is the relation between the tangent and secant?
Okay. So it's a good question. So let's say, what is a secant?
Sir, a chord which is produced outward.
Yeah. So depends on where that secant is, right? Now, sometimes there are questions which are asked like this. Let's say there is a tangent like this. Let's say there is a tangent like this. This is a chord. Okay. So here is a point A from where two tangents are drawn. Now, we have already discussed some parts of this, right? So you know that this OP is equal to OQ. You know that PAP is equal to AQ, right? So then you can always calculate the length of this PQ, length of this chord PQ.
Yes, sir.
So sometimes there are questions asked around this. Okay. If you have, let's say, another scenario where you have a circle like this, there is a secant here, and you draw a tangent from here. So this chord is extended to a point C, and there is a tangent P here. And this is the circle. So what do you know about this? You know that OP is right angle triangle. Okay. Now, if you join these two, can I say that OP is equal to OA is equal to OB?
Yes, sir.
Yes,
Because
sir.
all of them are radii only, right? So there might be questions asked around some geometrical properties here. Say they might ask you to calculate the length of the tangent. They might ask you to calculate the angles in the triangle which is formed and so on. So sometimes there might be a question like this. They might ask you, what is the angle subtended by this AB, side AB? Now, if you are able to calculate this angle, you can obviously calculate this angle as well. That is half of it. Or if you are able to calculate the angle at P, you will say that twice that angle is what is subtended at O.
Yes, sir.
So these are questions which can definitely be solved. All you need to do is be very careful when you draw the rough diagram. Every detail that is given in the question, if you are able to capture it in the diagram, then you will be able to solve any problem which is given.
Excuse me, sir.
Yes.
Sir, can you give any example of calculating the length of tangents?
Yeah, so calculating the length of a tangent. See this, if you take this scenario, Now I have mentioned that triangle OAP is a right angle triangle. Am I right? So here, what is the in this right angle triangle, can I say OA square is equal to OP square plus PA square?
Yes, sir.
Yes, sir.
OA square is the distance between point O and A. So I'm assuming you will know that, right? If the point A is given, you can calculate the distance between 2 points. Coordinate geometry, you would have studied that.
Yes, sir.
OP is nothing but the radius of the circle.
Yes, sir.
PA is the length of the tangent, right? So PA square will be equal to OA square minus R square, where R is the radius of the circle. So the length of the tangent PA will be equal to square root of OA square minus R square. Sometimes they might say the circle has a center at the origin and this A is at 3,4. So what will the distance OA be?
We will calculate by using distance formula.
Yeah, so you will say square
Okay.
root of x1 minus x2 squared plus y1 minus y2 squared, right? So just using the distance formula, you will be able to calculate OA. So once you know OA, once you are given the radius of the circle also, then you can calculate PA as well.
Excuse me, sir.
Yes.
Sir, if we are given the side PQ and we have to calculate R, are these type of questions also in exam?
Yes, you should be. Yeah. So you can calculate that also. See, if you observe this OPQ, isn't this a isosceles triangle?
Yes, sir.
Now we have also mentioned that in an isosceles triangle, this will be a right angle and this will be bisecting. This is also the perpendicular bisector.
Yes, sir.
Now, if you take this one small triangle here, you will be able to understand multiple properties of that, right?
Yes, sir.
So there might be questions which will be asked which are an extension of that or based on that. See, another interesting thing that you can look at is if you look at triangle OPA, okay, and if I have to calculate the area of this, can I write half base as AP into height as OP? Because they both are perpendicular, no?
Yes, sir.
Now, can I write this the same triangle as base as OA into height? Let's say this was the height. Let me name this point as PS.
Yes, sir.
Now here, if you observe, PS is something which you don't know. You
Yes,
know
sir.
AP, you know OP, you know OA. So by equating these two, you can calculate the value of PS.
Yes, sir.
And once you know the value of PS, can you say that double that will be the length PQ?
Yes, sir.
Yes, sir.
Yeah, so you can calculate the length of PQ also. Yes, any more questions? Great. Thank you, everyone, and see you all on the second. Over to you, Maitri.
Thank you, everyone. Thank you, Praveen. I think the session was quite interesting and very informative, seeing from the interaction the students have. I hope